Well, Bill, we're responding to a YouTube video that's getting quite a lot of views. It's called Physicists and Philosophers Reply to the Kalam Cosmological Argument, featuring Penrose, Hawking, and Guth. It fits neatly into 4 segments, so we decided to do a 4-part series in our podcast. We've dealt with the first philosophical argument in the first video, and then the second philosophical argument for the beginning of the universe in the second podcast. Today, we're going to look at the scientific evidence for the beginning of the universe, which they address next. Now, there's just no way that we can possibly respond to everything in the video, but we are playing the representative clips of this program. And Bill, you're also responding to this video in the Question of the Week feature. So our listeners and viewers can get more when they go to reasonablefaith.org. Here's the next excerpt from the video.
The infinite future is not the only infinity supporters of the Kalam tend to embrace. They've also claimed that the Big Bang singularity proves a beginning of time.
Arrives at a state of infinite density at some point in the finite past. This state represents a singularity at which space-time curvature, along with temperature, pressure, and density, becomes infinite. It therefore constitutes an edge or boundary to space-time itself.
The argument by Lane Craig that the fact that there's that the infinite past is impossible, and therefore that conception of the universe is untenable, is incompatible with their claim that there is a singular point at which the universe originates, because the properties of that singularity are entirely infinite.
Precisely what a singularity is, as John Barrow has forcefully emphasized, is something that involves a kind of actual infinity. For physical reasons, involves a kind of actual infinity. And this is precisely what these very same thinkers said that they were suspicious of. So to put it very bluntly and very crudely, are they trying to have their cake and eat it, accepting an actual infinity in one context while trying to dismiss it and being suspicious of it in another context?
The initial cosmological singularity is a mathematical artifact of the standard model. I take it to be an idealization. It's dispensable. Cosmologists often cut out the initial singularity so that the universe, though finite in the past, has no boundary point. Some cosmological models, like the Hartle-Hawking model, round off the initial part of space-time so that although the past is finite, it has no boundary point. Having a beginning does not entail having a boundary point. In any case, the singularity doesn't involve infinite quantities in the Cantorian sense, an actually infinite number of things. As Quentin Smith points out, it's really a case of division by zero. You have the mass of the universe over zero volume, which yields infinite density.
Here's the next clip where the narrator says she thinks that there is another problem with the Kalam cosmological argument.
A further problem for the Kalam argument is that it assumes an eternal universe would have had to traverse infinite time in order to get to a unique now. But in relativity, there is no such notion. Time is relative. In order to tackle this, Craig appeals to what is known as the Neo-Lorentzian interpretation of relativity, which does restore a unique sense of now.
Oh, Kevin, this is another red herring. Einstein's original formulation of special relativity involved ordinary three-dimensional objects enduring through time. It was wholly compatible with a tensed theory of time and temporal becoming. The tenseless space-time interpretation of Hermann Minkowski came a few years later. The soundness of the Kalam cosmological argument does not stand or fall with a neo-Lorentzian interpretation of relativity theory, even though that is my preferred view.
Next clip from Carlo Rovelli.
Discovery with Copernicus is that the Earth is not the center of the universe. Well, but you can always rethink the Earth you can imagine that you can add a center. Nobody prevents you from doing that. You just complicate life for yourself. And it's the same for special relativity. You can add a preferred reference frame. It's not visible, it's not detectable, but you think it's there. That's the Lorentzian, the neo-Lorentzian interpretation of special relativity. What do we gain? The only thing we gain is that we can do the new physics with old mindset. But I think we should adapt our intuition to the new physics, not adapt new physics to our intuition, right? When we discover that the Earth is round, that's up, that's down, but if you're in Sydney, it's the other way around. Well, you can think, yeah, but in reality, there's a true up and a true down. You can, but what do you gain? I mean, you have to adapt your intuition about up, down to the discovery, not the other way around. Physicists are not particularly keen about neo-Lorentzian interpretation of special relativity. Having said that when you go to general relativity, have a neo-Lorentzian interpretation is much harder, because in special relativity you just pick a frame and you. In general relativity there is no global frame. I think everything in physics, modern physics, is telling us that there is no preferred frame, there is no preferred time slice, there's no preferred time.
Notice that Rovelli admits that we can, with Lorentz, add a preferred reference frame. There is no scientific problem here. Rovelli's only objection is, what do we gain? Well, for my part, our gains are metaphysical, a more credible view of the world than that offered by the tenseless spacetime interpretation. But there are as well some prominent physicists like J.S. Bell, Franco Soleri, Antonio Valentini, and others who think that scientific gains are to be had as well. In particular, the so-called Bell inequalities seem to require a preferred reference frame. If anyone's interested in this, I'd recommend my two books, Time and the Metaphysics of Relativity, published by Kluwer Academic Publishers in 2001, and then my and Quentin Smith's anthology entitled Einstein, Relativity, and Absolute Simultaneity, both of which defend the view of a tensed theory of time in the context of relativity theory.
More from Carlo Rovelli in this next clip.
Craig has suggested there is a universal clock that gives us a unique now. That is cosmological time, the time since the Big Bang.
Cosmic time is the same for every hypothetical observer in the universe, regardless of his state of motion. In other words, cosmic time is a kind of reinstatement of Newton's absolute time.
Well, cosmological time is a fake. Why? Because matter, gravity slows time. So inside the galaxy, clocks go slower than outside. The point is there are many different clocks in the universe, which they don't agree with one another, and there are many times in the universe which don't agree with one another. The idea of the cosmological time is just one arbitrary definition of an average, but I can give a different definition of an average.
For shame. Rovelli knows that the slowing of clocks in a gravitational field has absolutely nothing to do with the time parameter that measures the duration of the universe. Cosmic time is not arbitrary, but rather it charts the evolution of so-called hypersurfaces of homogeneity.
Here's our next clip, Bill, and Alexander Vilenkin makes an appearance here.
I don't think anybody believes that the universe started off with the singularity. That just tells us that Einstein's classical theory of general relativity breaks down. So that classical theory of gravity doesn't apply when you get to very high energies. So it's replaced by some quantum theory, consistent quantum theory of gravity. String theory is a candidate.
Standard Big Bang cosmology, which was a hot Big Bang, right? You start with a very hot, dense universe, which begins at singularity. So that picture, I don't think anybody believes.
Right. So what becomes of the earlier objection that the singularity involves an actual infinite? I guess that wasn't really a problem after all, was it? As I said before, the beginning of the universe doesn't require a singular boundary point.
Here's the next clip.
Many scientists have taken our best candidates for a quantum theory of gravity and analyzed the Big Bang. Models inspired from string theory often show that the Big Bang was not the beginning, and a frequent result is that there was a contracting era that preceded our expanding universe.
There had been an evolution of the universe which was some kind of mirror image of what happened afterwards. So in the same way as the post-Big Bang era where we live, in our model will last forever, and I think it also lasts forever in ordinary inflation, okay? For us, because of this symmetry, this duality, also the past is infinite. Okay? The future and the past are both infinitely long.
String theory's main rival, loop quantum gravity, seems to show the same thing.
If you reverse the film, so to say, of the evolution of the universe and went back in time, the universe was contracting. And then, instead of reaching a zero volume, in fact, when it reached the curvature became Planckian, then new quantum effects come into the picture, and they cause the universe to bounce.
For an examination of string models, including Veneziano and Gasparini's pre-Big Bang inflationary model, as well as Steinhardt and Turok's cyclic ekpyrotic model, followed by an examination of loop quantum gravity models, including Bojewald's cyclic model and Ellis's asymptotic model, see the discussion by James Sinclair in our essay, The Kalam Cosmological Argument, in the Blackwell Companion to Natural Theology. As Alex Vilenkin has repeatedly emphasized, none of these models can be past eternal. In fact, it makes me wonder, Kevin, why didn't they ask Vilenkin about the viability of these models? Makes you think.
Exactly. Here's our next clip.
With the physics community abandoning its belief in the applicability of the Penrose-Hawking theorem, Kalam advocates switched to a newer theorem known as the Borda-Guth-Vilenkin theorem, or BGV. This theorem was developed because the period of rapid expansion, known as inflation, that's believed to have taken place in the early universe, violates one of the assumptions of the Penrose-Hawking theorem, that gravity is always attractive. Inflation is also thought to be eternal into the future, creating an infinite multiverse.
In 2003, Arvind Borde, Alan Guth, and Alexander Vilenkin were able to prove that any universe, which is on average in a state of cosmic expansion throughout its history, cannot be infinite in the past, but must have a past space-time boundary. What makes their proof so powerful is that it holds regardless of the physical description of the very early universe. So in fact, the Borde-Guth-Vilenkin theorem does imply an absolute beginning of the universe.
I was working with Arvind Borde and Alex Vilenkin to understand what we can learn about how inflation might have started and how far back it could have gone. And in particular, once we realized that inflation could be eternal into the future, it seemed like a very natural question to ask, could inflation have also been eternal into the past? And what we found was that inflation could not be eternal into the past. What we basically managed to achieve was proving a theorem which says that any expanding region of space-time that has some minimum expansion rate can only go back so far and not infinitely far. So that means that inflation must have had a beginning. It doesn't really say that the universe must have had a beginning, but it says that the universe could not have been expanding forever up until the present time.
Proving that the universe could not have been expanding forever up until the present time does imply a beginning unless you can craft a tenable model according to which the universe was previously contracting or was static prior to expansion, which has not been done.
And here's more from Vilenkin.
The theorem proves that inflation must have a beginning, right? The universe as a whole, the theorem doesn't say that. It says that the expansion of the universe must have a beginning, right? So, but it opens the door somewhat for alternatives.
This clip is so misleading. The Borde-Guth-Vilenkin theorem has the condition that the universe be on average in a state of expansion throughout its history. Bouncing or cyclical models may not satisfy that condition, and so they are not excluded by the theorem. But as Vilenkin has repeatedly explained, such models face other insuperable obstacles that preclude the universe's being past eternal. And so again, I wonder, Kevin, why didn't the producers of this video ask Vilenkin about that?
And here's the narrator talking about one way to avoid the BGV.
As we've seen, one way to avoid the BGV is to have a past contracting universe, which is also a common prediction in multiple approaches to quantum gravity. But some suggest that this collapsing phase will be messy and unstable, and therefore not be able to transition to our smooth, homogeneous universe.
Right. This is exactly what Vilenkin says. It's funny that they never asked him to explain it to them.
Here's our next excerpt.
We have absolutely no idea of what exists in the universe before the bounce. So it's very speculative and very difficult to decide whether the situation is stable or not. And even in the case where the situation is unstable, usually what it means is that the simplifications we use in standard cosmology cannot be used anymore. But you know, nature doesn't care about the fact that it is hard to calculate. So when we say that something doesn't work, most of the time it means that the model we use to describe these things doesn't work anymore. For example, you cannot use the Friedman equation because the universe is so inhomogeneous that the Friedman equation is not usable anymore. So what? The universe doesn't care that we have to invent another equation. I think the correct way to think is not to go from the past to the future, is to start from what we know. What we know is what we see around us today. The universe is expanding. We have stars, we have galaxies, we have gravity. We have a theory. And then we go backward in time and we see what happened. And in our theory, when we go backward in time, we do not end up with a singularity. We end up with a bounce.
This is mere hand-waving, an appeal to the unknown. The bounce needs to result in the low entropy condition of our early universe. Vilenkin and others have shown that that cannot happen. So, beginning from what we know, where we are, we go backwards in time and we find that you cannot get here from there. And even if we could, postulating an earlier contraction does nothing in itself to restore a past eternal universe.
Okay. In this next clip, they discuss another theorem developed by Aaron Wall.
With the authors of the BGV explicitly stating it does not prove the universe had a beginning, the Kalam advocates have begun using yet another theorem developed by Aaron Wall.
Wall is assuming that some version of second law of thermodynamics is really fundamental and should be a fundamental ingredient in this series which determine whether there will be singularity or not. And I agree with that. I think that it really is something that would emerge in approximate sense in a semi-classical regime.
Generalized second law that was proven by Aaron Wall for a quantum singularity, it assumes an infinite space. And if you don't allow for infinities in your theory, then you cannot take that theorem seriously either.
Well, Kevin, why do you suppose they didn't go to the source and ask Aaron Wall himself about this? I think we're seeing a lack of objectivity on the part of the producers of this video. So I did go to Wall and ask him. And he tells me that while his generalized second law of thermodynamics implies an initial cosmological singularity in an infinite space, nevertheless, in a finite space, at some time t in the past, the generalized second law would simply reduce to the ordinary second law of thermodynamics. And then he says you can still argue from the ordinary second law of thermodynamics that most likely either A, the universe had a geometrical beginning, or B, the arrow of time must have reversed at some time in the past. In the latter case, one still has a beginning of the universe since both time directions are future-oriented.
You always do your homework, Bill. Here's
Thank you.
Here's the
Thank
next
you.
clip.
Craig also quotes a paper by Anthony Aguirre and John Cahias that he claims closes the door to a past eternal quantum gravity era. But in most models, the quantum gravity era is brief anyway. And the paper only referred to a particular model known as the emergent universe.
Now, I quoted Aguirre and Cahias simply to show that a quantum state cannot persist changelessly from eternity past and then produce a new effect. And what he says in the next clip confirms that.
Let's go to the next clip.
But there are other possibilities too, as to how the universe could be in accord with the Bordet-Guth-Vilenkin theorem, but could, I think, really be past eternal. If you define a past eternal model, you can. It self-consistently works, but you do have an edge to it. If you can ask what's beyond that edge, and it's another copy of the same universe. So I think where the debate lies, past eternal models exist. I think some of them are flawed, like the emergent model. I think you can't really make a self-consistent model that stands up. Past eternal inflation or the steady state model, I think you can, but you have to do it carefully. And there's an interesting then answer to what is this Bordet-Guth-Vilenkin theorem pointing to? It's pointing to something very interesting. It's just not in initial time.
Jim Sinclair has already responded to these proposals in his Blackwell companion article. In brief, it's more plausible to interpret the Bordet-Guth-Vilenkin theorem as Vilenkin does, as implying a beginning of the universe, than to try to save a past eternal universe by postulating two non-interacting universes at some past boundary or a reversal of time's arrow at some point in the past.
The narrator begins this next clip.
Just as there are theorems that prove the universe had a beginning, there are also theorems that imply the opposite.
I think you can prove anything. Theorems are very strange things because you can have a theorem to prove anything as long as you assume the right things. In a way, that's the problem. And you can violate any theorem as long as you violate the assumptions.
Pardon me, but you can't prove just anything. Your assumptions must be credible in light of the evidence. The Bordet-Guth-Vilenkin theorem rests on the single, unremarkable assumption that the universe is, on average, expanding throughout its history. If it's not, then the theorem doesn't hold. But in that case, as Vilenkin has said again and again and again, you encounter other insuperable problems that preclude a past eternal universe.
Let's go to the next clip.
Of course, there are the singularity theorems, but you can always interpret them as telling you that a quantum theory of gravity should not have one of the hypotheses that you are using to formulate this theorem.
Fine, so bring on the quantum gravity models like the Hartle-Hawking model or the Vilenkin model, both of which involve a beginning. Quantum gravity doesn't restore an infinite past. As will come up later, I think, the question will be rather whether, according to these models, the universe can come into being from nothing as both Hawking and Vilenkin suggest.
Well, Bill, that's what we're going to talk about next time in this exciting series on the next podcast, The Need for a Cause. That's on the next Reasonable Faith with Dr. William Lane Craig.